A 500-gram block of ice is dropped into 1 kilogram of an unknown substance. The ice is at 0 degrees Celsius while the liquid is at 30 degrees Celsius. If the liquid does not change phases, what is the specific heat of an unknown liquid if the final temperature is 20 degrees Celsius? So we have our 500 kilogram block of ice and our 1 kilogram of liquid. The ice is at 0 degrees Celsius and it's solid, while the liquid is at 30 degrees Celsius. The heat from the liquid is going to go into the ice until the temperature between the ice and the liquid are exactly the same. So before we start solving this problem, we need to know a couple things. We know these two equations here. The first equation is within a phase, the amount of energy needed to heat up an object. And this equation here is when you're changing phases. So in both equations, Q stands for the amount of heat there is, and heat is measured in joules. M stands for the mass of the object in kilograms. C stands for the specific heat of an object. Delta T stands for the change in temperature in an object, from the difference between the initial and the final temperature. And L stands for the latent heat of an object. Now when we're talking about water, there's two different specific heats. There's ice, which is 2,100 joules per kilogram degrees Celsius. And then there's water, which is 4,180 joules per kilogram degrees Celsius. For latent heat, we have from ice to water, so when it's turning from the solid form to the liquid form, we have 3.33 10 to the 5th joules per kilogram. And from water to steam, so liquid to gas, it's 22.6 10 to the 5th joules per kilogram. Another thing we need to know is the law of conservation of energy. Energy cannot be created or destroyed, so we can't just have random energy be added to this equation. So because we don't know anything about the unknown liquid, we're going to have to start with the ice. Now we know both the specific heat and the latent heat of ice. Now the block of ice is at 0 degrees Celsius, and ice melts at 0 degrees Celsius, so we don't have to lower the temperature at all. So now we can change phases. Now, because we're changing phases, we're going to use this equation with the latent heat in it, and we're going to see how much energy it takes to turn ice to water, or 500 grams of ice to water. Now 500 grams is 0.5 kilograms, and 0.5 times 3.33 10 to the 5th joules per kilogram turns out to be 166,500 joules. Now the 3.3, like I said, is the latent heat of ice to water. Now because we found out how many joules it takes to melt that block of ice into water, we're gonna have to find how many kilograms, how much energy it takes to heat up the water. Now we're gonna have, again, the same amount of ice, but this time it's going to be the specific heat, which is 4,180 joules per kilogram degrees Celsius, times delta T, which would be the change in temperature, and the initials 0 degrees Celsius, the finals 20 degrees Celsius. So the change is 20. Now the kilograms and the degrees Celsius cancel out, and we're left with 41,800 joules. Now you notice that both these numbers are positive, and the reason why is because the ice is taking in joules. It's using joules to heat up. Now if we are cooling something down, joules will be removed from it. So when we add both these numbers up, we get a total of 208,300 joules. Now the reason why this is so important is because we know how much joules it takes to turn the block of ice into liquid at 20 degrees Celsius. And we also know the conservation, or law of conservation of energy, that energy cannot be created or destroyed, so that energy has to come from somewhere. So now we know how much energy it takes to melt the block of ice into a liquid and raise that liquid to 20 degrees Celsius. We know how much energy the unknown liquid has to give off. So we're not going to use ml, Q equals ml, because we don't need to know the latent heat, and the unknown substance never changes phases. It stays as a liquid form. And so we're going to use the equation Q equals mc delta T. However, we're not finding Q, we're finding C. So we're going to turn this equation into C equals Q over m delta T. And using that, we can figure out the specific heat. Now, if you notice here, the total heat is negative and the temperature is negative. Now, the reason for this is that the unknown liquid is actually losing energy because the ice is taking it and warming up. So the energy has to be negative. And the negative 10 degrees Celsius is because, well, it starts at 30 degrees Celsius, then lowers down to 20 degrees Celsius. So it actually loses temperature. So both those numbers have to be negative. And there's only 1 kilogram of the unknown substance. So if you solve that out, you get 20,830 joules per kilogram, degrees Celsius.